What's something people don't know about the silent language shaping our world? Imagine a world without computers, a world where the hum of a typewriter is the only sound in an office and the clatter of keys is the rhythm of productivity. No smartphones, no internet, no digital wonders that permeate our lives. Communication was slower, information was harder to access, and entertainment was a shared experience, often enjoyed in the company of family and friends. This was our reality not so long ago. Streets were filled with people engrossed in face-to-face conversations, parks were places of leisure without the distraction of screens, and daily life moved at a more deliberate pace. The digital revolution, with its transformative power, hinges on a fundamental element: computer code. These early machines, massive and cumbersome, were the first to be programmed, setting the stage for the digital age. This silent language, written by humans and understood by machines, is the invisible force shaping our modern world. Each line of code is a building block, a piece of the puzzle that brings our digital experiences to life. From the apps we use to the cars we drive, code is the underlying architecture of the digital age. It powers our smartphones, controls our smart homes, and even helps us navigate the roads with precision. It's the language that allows us to communicate with machines, instructing them to perform tasks, process information, and connect us across continents in the blink of an eye. Through code, we have created a global village, where distance is no longer a barrier to connection. Understanding the evolution of code is akin to understanding the evolution of the digital world itself, a journey marked by innovation, ingenuity, and the relentless pursuit of progress. From the earliest programming languages to the sophisticated algorithms of today, each step has brought us closer to a more interconnected world. The story of code is a human story, a testament to our ability to translate abstract thought into concrete instructions that drive technological advancement. It's a narrative of creativity, problem-solving, and the desire to push the boundaries of what is possible. It's a story that began over a century ago with a visionary mathematician who saw the potential of machines to transcend mere calculation and become tools of creative expression. Charles Babbage, often called the father of the computer, laid the groundwork for the digital revolution with his designs for the analytical engine. Alongside Babbage was Ada Lovelace, who is credited with writing the first algorithm intended for a machine. Her foresight and imagination helped to envision a future where machines could perform complex tasks beyond simple arithmetic. Today, the legacy of these pioneers lives on in the work of countless programmers and developers around the world. They continue to build on the foundations laid by Babbage and Lovelace, creating the software and systems that drive our modern lives. As we look to the future, the silent language of code will continue to evolve, unlocking new possibilities and transforming our world in ways we can only begin to imagine. From artificial intelligence to virtual reality, the potential of code is limitless, and its impact on our lives will only grow. In this ever-changing digital landscape, understanding the language of code is more important than ever. It empowers us to shape the future, to innovate, and to connect in ways that were once the stuff of science fiction. The silent language shaping our world is a testament to human ingenuity and the boundless possibilities of the digital age. What's something people don't know about the origins of computer programming? Ada Lovelace, an English mathematician, dared to imagine the future of computation. Working with Charles Babbage, the inventor of the analytical engine, a mechanical general-purpose computer, Lovelace wrote what is considered the first algorithm intended to be processed by a machine. Lovelace envisioned a future where machines could manipulate symbols, not just numbers, paving the way for the concept of a computer program. Her work on the analytical engine, though never fully realized during her lifetime, laid the groundwork for the development of computer programming as we know it. Her legacy as the first computer programmer continues to inspire generations of computer scientists and programmers. Ada Lovelace's story is a reminder that innovation often stems from daring to imagine beyond the confines of the present, to envision possibilities that others might deem impossible. Why are there not more people talking about the symphony of punched cards? The early to mid-20th century saw the rise of computers as we recognize them today. These early machines, however, were behemoths, often occupying entire rooms and requiring specialized knowledge to operate. Programming these early computers involved feeding them instructions through punched cards, each hole representing a specific command or data. These cards, while rudimentary by today's standards, represented a significant leap forward. They allowed programmers to create sequences of instructions, essentially early forms of programs that the computer could execute. The process was laborious and error-prone, requiring meticulous attention to detail. The whirring and clicking of card readers became the soundtrack of early computing, a testament to the dedication and ingenuity of those pioneers who painstakingly programmed these early machines. While punched cards have long been replaced by more sophisticated input methods, they serve as a reminder of the evolution of programming, from its humble beginnings to the sophisticated languages we use today. What I wish I knew at the start of my programming journey, instead of struggling with machine code. As computers evolved, so too did the need for more efficient ways to program them. Early computers were programmed using machine code, a series of binary digits that directly controlled the hardware. This method was not only cumbersome but also highly prone to errors. This led to the development of assembly language in the 1950s, a low-level programming language that uses mnemonic codes to represent machine instructions. These mnemonic codes were abbreviations or symbols that made it easier for humans to understand and write programs. Assembly language provided a more human-readable way to program computers compared to the binary code they ultimately understood. Instead of writing long strings of zeros and ones, programmers could use short, meaningful codes. Programmers could now use short, memorable codes to represent operations like addition, subtraction, or data storage, making the programming process less tedious and error-prone. For example, instead of writing a complex binary sequence to add two numbers, a programmer could simply use the mnemonic ADD. While assembly language represented a significant step forward, it was still a far cry from the high-level languages we use today. High-level languages, such as Python or Java, allow programmers to write instructions in a more natural, human-readable form. Programming in assembly language required a deep understanding of the computer's architecture and was specific to a particular type of processor. This meant that a program written for one type of computer might not work on another without significant modifications. Nonetheless, it laid the foundation for the development of more sophisticated programming languages that would allow programmers to focus on solving problems rather than grappling with the intricacies of machine code. These advancements paved the way for the creation of compilers and interpreters, tools that translate high-level code into machine code, further simplifying the programming process. Today, the legacy of assembly language lives on. While it is rarely used for everyday programming, it remains an essential tool for understanding how computers work at a fundamental level. It is still used in situations where performance and efficiency are critical, such as in embedded systems and real-time computing. As we continue to push the boundaries of technology, the principles established by early assembly language programming continue to influence modern computing. Understanding these roots helps us appreciate the incredible advancements we've made and the potential for future innovations. You need to hear this if you're a programmer or tech enthusiast. The late 1950s and 1960s witnessed a paradigm shift in the world of programming with the advent of high-level languages. These languages were designed to be more user-friendly and closer to human language, making programming more accessible to a broader range of people. Languages like Fortran, or formula translation, were among the first to be developed. Fortran was specifically created for scientific and engineering computations, making it easier for scientists and engineers to write programs that could perform complex mathematical calculations. COBOL, which stands for Common Business-Oriented Language, was another significant high-level language that emerged during this period. COBOL was designed for business applications, focusing on data processing and file management, which were critical for business operations. Lisp, short for list processing, was developed with a different focus. It introduced a unique approach to programming where code and data were treated interchangeably. This made Lisp particularly powerful for artificial intelligence research, as it allowed for more flexible and dynamic programming. Fortran, as its name suggests, was developed for scientific and engineering computations. It introduced features like loops and conditional statements that simplified complex calculations, making it easier for scientists to write programs that could solve complex mathematical problems. The introduction of these features in Fortran marked a significant advancement in programming as it allowed for more efficient and effective computation. COBOL, on the other hand, was designed for business applications. It focused on data processing and file management, which were essential for business operations. COBOL's syntax was designed to be readable and understandable, even by those who were not professional programmers. This made COBOL an ideal language for business environments, where it was used to manage large amounts of data and automate business processes. Lisp, with its unique approach to code as data, became a cornerstone of artificial intelligence research. Its flexibility and dynamic nature made it an ideal language for developing AI algorithms and systems. These high-level languages abstracted away much of the low-level complexity of interacting with computer hardware. This abstraction allowed programmers to focus on solving problems in their respective domains, rather than getting bogged down by the intricacies of the hardware. The development of these languages marked a turning point in the history of programming. They made programming more accessible and efficient, paving the way for the development of even more powerful and specialized languages in the future. This period of innovation laid the foundation for the modern programming landscape, where high-level languages continue to evolve and adapt to new challenges and technologies. The legacy of Fortran, COBOL, and Lisp can still be seen today as they have influenced the design and development of many contemporary programming languages. Their impact on the field of computer science is undeniable, and their contributions continue to shape the way we think about and approach programming.
Hit that like button, subscribe, and stay informed.